Okay, shall we continue? So in the earlier session we had discussed about impulse momentum equation. So what was the conclusion of that equation? It was like this: summation of all the forces in x direction or force in the x direction will be equals to rho into q into v2x minus v1x. This is what the equation was. Okay, so here what is a rho into q? I'll just try to explain it. Okay, so rho is, what is the unit of rho? Rho unit is kg per meter cube. So what is the unit for discharge? Discharge, it is meter cube per second. Okay, so if I multiply rho into q, it will be nothing but kg per second. So kg is representing the mass and second is the time, right? So rho into q is nothing but mass of fluid, any fluid. Okay, that is striking. I'm calling it as striking because here I'll just explain it later. Okay, striking per second. Okay, this will be given by rho into q. What is rho? Rho is the density of the fluid which is flowing and q is the discharge. So mass of water striking per second is nothing but rho into q. You just keep this in mind. Okay, now I will explain you some of the things which we want to understand. Okay, now imagine this is some surface. Okay, on this surface if I apply the jet of water, so you know that there is some impact that is going to take place on this plate or on this board, right? So in order to find out that, this is the equation we have. Okay, so in this equation, imagine if I am throwing it with water, if I am applying the jet with the water. Okay, so there, what is the density here? The density is nothing but the density of the water. What is discharge? Discharge we have to find out, right? So if I know what is the density of the fluid, if I know the discharge, and then v2x minus v1x will give you the resultant force in the x direction, right? So that is what we want to find out here. So basically we used to solve for flat plane, inclined plane and all of those. Okay, now we usually what do is that we want to find out how much is the impact of the jet that is taking place on any face, right? It may be flat plate or it may be inclined plate, but for your syllabus we only have circular vanes. Okay, I'll just try to explain what is circular vane is. Vane and curved vanes. Okay, let us consider this. Okay, this attendance sheet that I have in hand, it is actually flat, right? The reason why it is flexible, I am using it as a condition. Okay, now if I keep it completely vertical, it is a flat plate now. On the flat plate the jet is sitting. Okay, if I make it inclined, so it is inclined plane. Is clear? Now I am just making it as a curve. Okay, this is my curved vane. Okay, so imagine if this is curved vane, on the curved vane if the jet hits, what will be the reaction? How much is the force being exerted? We want to find out. Okay, now there are two types of curved vanes. One is symmetrical curved vanes, the other one is unsymmetrical curved vanes. So what we'll do is, first we will try to understand what is symmetrical curved vanes. Okay, later we will try to understand what is unsymmetrical curved vanes. Okay. So I'll just show you the example of two. The first diagram is represented by symmetrically curved vane. The second diagram is represented by unsymmetrical curved vane. Okay. Now you try to imagine this. You are not normal to this face, but I'll try to keep it. Okay. Now you can see that this angle, which is included angle. Okay. If I take the included angle and if it remains same on both the end, this is one end and this is the other end. So if I take the tangent at both the end, if I join here, and this included angle will be divided by 2, and then you find out that these two angles are remaining equivalent to the included angle, half of the included angle, then I can say it is symmetric. Okay, that's what the condition of symmetry is. Now if you go to see this figure, in this figure what is happening, this angle which I have drawn the tangent at the inlet, I'll call it as inlet, I'll call it as outlet. Okay, so at inlet you can see how much is this angle is equals to theta, but at the outlet it is equals to phi. You can see that the angle here, the tangent that are drawn here are not same, they are different. Okay, so this theta and this is phi, so theta is not equivalent to phi, right? But in this case what is happening, theta is equivalent to theta, so that's why both the angles at the inlet and the outlet are remaining same. So this case we call it as symmetric condition, this we call it as unsymmetric condition. Now you can strike the jet in two ways. What is the two ways? I can strike the jet exactly at the center, and I can strike the jet exactly tangent to one of its side. For example, I can strike the jet exactly at the center of the symmetrical curved vane, or else I can strike it across one of the tangent direction to one of its tip. This is one tip, consider this as the other tip. Now we'll try to see the behavior in which the water will flow. If I strike it normal or perpendicular to this curved vane, so what will happen, the water hits like this and then it splashes outside like this, right? This is what the condition if I hit it at the center. Now if I hit it tangentially, what will happen, the water will slide over this vane and it moves like this. Okay, so that's why I'm calling it as inlet tip and I'm calling it as outlet tip, right? So this is what the symmetrical and unsymmetrical curved vanes, right? So I hope this is clear. Now what we'll do is we'll try to understand what is the force being exerted on the symmetrically curved vane. Here we are discussing about symmetrically curved vane, not unsymmetrical vane. So if it is symmetrically curved vane, I told you earlier what is the condition of symmetrically curved vane. This angle here theta and this angle here theta will remain same, they will not change, right? So now we need to calculate how much is the mass of water striking per second. What is rho into q? Rho into q is nothing but, as I explained you, mass of water that is striking per second. So to calculate rho and q, we must calculate discharge. Discharge is what? Discharge is given by q is equals to a into v. So what is a? A is the jet. Assume the diagram that is showing here, this is some jet, it has got a nozzle and nozzle had got some diameter. So assume d is the diameter of the nozzle. I can calculate how much is the I can calculate how much is the area of the nozzle. So if the area of the nozzle is multiplied with the velocity with which it is coming, it will give you the discharge. If you know the discharge, if you know what is the type of fluid, okay, if you know the fluid, here basically the fluid will be water itself, right? So density of water multiplied by discharge will give you the mass of water that is striking per second. Instead of fluid, you can also consider this as water, because basically we will discuss only water in the coming case. We will not discuss about any other fluid. So this is what the mass of water that is striking the vane per second, which is rho AV. Rho AV is nothing but rho into q itself, where A is the area of the nozzle, V is the velocity, that is velocity of water that is coming out of the nozzle. Right? Now let us calculate what is V2x and V1x. Okay, you can take your time if you want to observe what is V2x and V1x. So this is the curved vane I have, and how the water is hitting. Water is hitting like this, okay, and the water comes out like this. Is this clear? Okay. Now there is a slight change that we have done in order to calculate the force exerted, right? So instead of V2x minus V1x, we are considered V1x minus V2x, because we are trying to find out how much is the impact on the plate. Okay, so while calculating the impact on the plate, what we do is that we reverse this condition. Okay, V1x minus V2x will do it. Okay, so that's why, what is the velocity with which it is entering? What is the initial velocity? Initial velocity, which is V1x is equals to V. Okay, now how much is the velocity that is going outside, which is also same, V itself. Is this correct or not? Assume that this entire surface is very smooth. So what happens? The water strikes here and it glides over the other surface. So the velocity will remain same. Only if this surface is rough, what will happen is the velocity get reduced because of the friction. So assume that the curved vane is entirely smooth, so that's why the velocity with which it hits here and it comes out here will remain same. But the condition here is, you can see here, the direction of velocity is not remaining same. The direction of velocity is not remaining same. So I want to calculate how much is the component of velocity in the x direction. I want to calculate this. So how do you calculate this? Assume this is, what is this angle? This angle is theta. So can you find out how much is the component in the x direction? The component in the x direction will be equals to v into cos of theta. I have already written here, but I am just explaining it again. Okay. So what will be v2x here? v2x will be equals to v into cos of theta. Is it done? Now going back to this equation, in this equation I will substitute all of this. Fx equals to rho into q into v2x means what? Sorry, v1x means what? V. I changed it. I told you already, I have shifted these two. I shifted it because I am trying to find out how much is the impact of jet on the curved vane. Okay, I am not calculating how much is the force of the jet, right? So that's why. So v1x is v minus of. Okay, now tell me whether the direction of the jet when it entered and the direction of the jet when it get exited are remaining same. No, right? So the direction of entry is like this, the direction of exit is opposite to it. So that's why I have to consider this as minus. Okay, so that's why minus of v cos of theta, right? So what will this become? So we already know rho into q is nothing but rho a v, and let us bring v outside, so it will become rho a v square. This will become minus into minus plus, so 1 plus of cos of theta. So this is the equation to calculate the force exerted on the curved vane when it is symmetric and the jet is hitting normal. Okay, what is this? Rho is the density, a is the area of the nozzle, v is the velocity with which it comes, and theta is the angle. Okay, so if we know all of this, we can calculate how much is the force exerted. Okay, any doubt in this part? So you observe this entire equation, you try to comprehend this. Once you have understood everything, if you have any doubt, you can ask me, I'll clarify this. Very good. At least idorra consistent adarla. Sir, innೊಂದು pen ಕೊಟ್ಟನ. ಅರ್ಥ ಆಗುತ್ತಾ? ಇಲ್ಲ, ನಡೀತದೆ, ಹೀಗೆ ಕಂಟಿನ್ಯೂ ಮಾಡ್ಬಿಡೋಣ. ಮತ್ತೆ ಕಂಟಿನ್ಯೂ ಮಾಡಲೇ? ಓಕೆ, ಶಾಲ್ ಐ ಕಂಟಿನ್ಯೂ? If you want me to continue, I'll continue it. Any one of you please give a thumbs up or wave or anything. We'll continue? Okay, very good. Thank you very much. Till now, this curved vane was stationary. Stationary means what? It was not moving. It was on a given position. It was not changing its position. Now imagine this curved vane was there and we were hitting with the water jet. Okay, now if this curved vane moves, this constantly moving with some velocity, and the jet is also hitting, so then what happens is we need to find out how much is the force exerted on the curved vane when it was moving. Okay, in earlier case it was stationary, it was in one single position. Now the plate is moving. When it is moving, we have to change a little bit. So what is that change happens? I'll explain you. Okay, imagine this is the curved vane. Okay, now this curved vane is moving with a velocity called u. Okay, so if it is moving with velocity, after some point what happens is that it changes its position like this. Okay, so here what is the velocity with which the jet is hitting? It is with a velocity called v. Okay, with what velocity the vane is moving? It is moving with a velocity called u. Then we have to consider the relative velocity. What is relative velocity? Relative velocity is equals to v minus of u. Okay, now when you are going for v minus u, resultant velocity is equals to what? V minus u. Now what will be the change that will happen in the equation? I'll write here. Okay, so here fx equals to, we all know, rho into q. This is equals to v1x minus of v2x. Why we are done v1x minus v2x? I explained it earlier. So again going back to find out what is v1x. Okay, so v1x is equals to, So here in the earlier example I have considered velocity of the jet. So what we have to consider here is also the velocity with which the vane is moving. This vane is moving with a velocity called u, right? So here v1x is nothing but vr. What is vr is? Vr is nothing but v minus u. What is v? V is the velocity of the jet, u is the velocity of the moving vane. So v1x is equals to vr is equals to v minus u. Now what will be v2x? V2x will be Vr into cos of theta, right? So this will be equals to V minus U into whole cos of theta. Is this correct? Now this is what the equation we had. Now what will be Fx equals to rho into Q into, we already know what is this. V1 is equals to V minus U minus of minus V minus U into cos of theta, right? So this will be equal to rho Q into V minus U into 1 plus of cos of theta. This will be the equation for Fx. When this condition will be used, when this equation will be used, this equation will be used in case of moving curved vane. Moving curved vane. Okay, and what is the direction of the jet that is hitting? The jet is hitting normal. Okay, and the vane is symmetrical curved vane. Okay, so you can write this down if you want to note it. So if you have any doubt, I'll explain this equation again. If you do not have any doubt, I'll move on to the next condition. Okay, so what was the first condition? First condition was to calculate how much is the force exerted on a curved vane when it is stationary. In the second case was to find out the force exerted on a curved vane when the vane is moving with a velocity called u. For your understanding, the blue pen that I used is for the equation to calculate the moving vane, and all the red equations that I written are for stationary condition.